In single variable calculus, the chain rule is the formula that we use to calculate the derivative of a function when you have one function inside of another one. An example of such a function is sin of x squared. Most students remember this as there being an inside function and an outside function, and the calculation of this should be basically automatic. But as a reminder, this is technically a composition of functions. If f of x equals sin of x and g of x equals x squared, then f of g of x is sine of x squared. And applying the chain rule formula directly is how we get the result. The idea of the chain rule is that you're trying to figure out how the function f changes as the variable x changes, but there's a function that's changing in between them. The variable x changes the function g, and the changes of g impact how f changes. In the previous section, we saw how the changes of a two-variable function depend on what's happening in the x direction and in the y direction, and the changes in each direction may be different. So we need to incorporate all of that information into our formula. Let's be a bit more specific. Imagine a person hiking along a trail, and let's think about how we might model their elevation above sea level over time. If we imagine looking down from the sky, the trail creates a path that can be modeled in the xy plane. The hiker's position would then be a function of time, and we can denote the time axis as a horizontal line. At any moment of time, the hiker is somewhere along the trail. This creates a function from the variable t into the xy plane. Furthermore, at any given location, the trail is at a certain elevation. This creates a function from the xy plane to the variable z, which we'll put off to the side. As the hiker moves along the trail, their elevation goes up and down along that axis. This is a composition of functions. At any given time, the hiker is in some location. At any location, there is an elevation. So at any given time, the hiker is at some elevation. If we pick multiple time values, we get multiple elevations, and this gives us the outline of the graph of elevation at any given time. Now let's think about how the elevation changes with time. Clearly, if the hiker is moving faster, the elevation is changing faster. But the change of elevation also depends on the shape of the path. Running up a steep slope will lead to a faster change of elevation than walking along a gentle grade. So the change of elevation with respect to time needs to incorporate both elements. Here's the formula for the chain rule. Let's try to understand the individual pieces. On the left we have the derivative dz dt. This is the rate of change of the hiker's elevation with respect to time. On the right we have two terms. The first term is the change of elevation due to motion in the x direction, and the second term is a change of elevation due to motion in the y direction. The partial derivative terms give us the slopes of the terrain in each direction, and the time derivative terms are speeds. It's the combination of slope and how fast you're moving that gives the change in elevation. And that's the basic intuition of the chain rule. We're breaking up the change of the function z into changes that can be attributed to movement in the x direction and the y direction. The chain rule can feel confusing because there are often 4 or more variables in the problem at the same time, and so it is helpful to have a scheme to organize that information in a helpful way. The section on tree diagrams is supposed to help with that. The core idea is that we're keeping track of the relationships between variables. A tree is a type of mathematical graph that can be used to represent those relationships. At the top of the tree, we have the outermost function, and as we work our way down the tree, we're keeping track of the internal dependencies. Here's a tree diagram for the function we were just working with. Notice that z is at the top, and that z is a function of x and y. This is the statement that our altitude depends on our location. But we can see that x and y are functions of t. This is the statement that our position depends on what time it is. So as we read down the tree, the branches show us the variable dependencies. Each of the connecting bars represents a derivative. It's the derivative of the top variable with respect to the bottom variable. You have to decide whether it's a regular derivative or a partial derivative, and that simply depends on whether the top function has one or more branches sticking out of it. So the top left branch is partial z partial x. The top right branch is partial z partial y. The two bottom branches are the regular derivatives dx dt and dy dt, since the variables x and y only have one variable of dependency. To construct the derivative dz dt, we simply find all the places where t is at the bottom of the tree, multiply all the derivatives along connections going back up to the top, and then add the results together. We can see that there's a left path and a right path. On the left path, we have partial z partial x multiplied by dx dt. On the right path, we have partial z partial y multiplied by dy dt. This is a situation where a simpler example feels more complicated because it's hard to see what's actually happening. So we're going to look at a more complex situation. Here's another tree diagram. In this case, the function w depends on three variables x, y, and z. And each of these depends on the variables s and t. This means that we can view w as a function of the two variables s and t. How can we calculate the partial derivative of w with respect to s? We'll start by identifying all of the places where s is at the bottom of the diagram. This gives us a number of branches to trace up to the top. For each of these branches, we write down the corresponding derivatives. We then multiply the derivatives that are along the same paths and then add the results. The same idea would hold if we had another layer of dependency, and this gives us a strong hint as to the value of organizing the information in this way. Imagine if you had to simply memorize a bunch of different formulas to account for all the different relationships between the variables. It would be very difficult. One of the key ideas as you get further along in math is to understand patterns and relationships more deeply. This helps us to make connections between ideas and allows us to gain a deeper understanding of and appreciation for the concepts that we're working with. As we continue moving forward in this class, I hope that you will make some time to think beyond what's immediately in front of you and try to relate what you're studying to things you've seen previously in your mathematical experiences. This will really help you grow as a student of mathematics, and it's a practice that will help you in the long run.